Good morning, everyone. I am Mr. Ish. Thank you for joining me for this introducing curve rotations video. Rotation of curves and volume of curves which arise due to dynamic movement of a curve about a line of axis or a line of rotation is among my favorite subjects or topic matters when it comes to calculus. And it's about time we present at least one video here to at least start jogging our minds with this whole concept of curve rotations and volumes. It's not a difficult topic to understand once you understand the basic fundamentals of this. If you have a given function, and what we will do in this video is do everything in a very basic and simplified manner. Let's just call this function right here y is equal to x. You know, it's a linear line which extends here to the origin exactly as you see it. To rotate this around an x-axis, you know, here's my x-axis right here, and we were to rotate this line, we were to limit the domain of this y equals x from 0 to 1. Essentially, you'd be looking at it here from 0 up to 1. You'd be looking at this portion right over here, and you were to rotate that. Depending on what you are starting out with regards to your initial function, you can have two types of things arise. Cross sections is what I mean. Let's show you what those are. So when you look here at your curve y equals x from a lower limit 0 to 1, we're essentially looking right over here. If you were to do the movement of this, what you would end up getting is a three-dimensional cone that would arise. Think about it. You're looking only here from 0 to 1, and you're rotating around the x-axis, and then you develop a three-dimensional cone, and that's exactly what you end up having. A single line having two dimensions by means of this dynamic rotation around the x-axis, right? You end up getting a three-dimensional structure for which a volume can be determined. If you were to look at a cross-section over here, you'd end up getting a cross-sectional slice. This slice would be called a disk. This disk would have a certain radius. That radius would give you a certain area, which is your pi r square. And you can see very well, here's a three-dimensional disk which is arising. But when you're talking about volumes and curves and rotations, you're looking at something which looks like this. From a lower limit to an upper limit, you're doing cross-sectional slices being added up from a lower limit to an upper limit. You add up all of these cross-sectional slice areas. When you add them all up, you get a volume. But the most difficult and important part over here is to determine what the radius is, because that radius will feed right here into this formula. The radius is usually what your original formula is. Y equals x. Here my radius is any point from your line of axis, which is your x-axis, shooting up towards your curve, and that radius happens to be an x. Hence this area becomes pi x square. This becomes this portion right over here, which you integrate from a 0 to 1 to determine this volume. And we're looking here everything along an x-axis, so therefore everything is dx. Your intervals are along the x-axis or a horizontal line. You have a pi x squared dx. The pi can be pushed out as a coefficient. You have x squared dx. This is a very easy integration. You get pi x cubed over 3 from an upper limit 1 and 0, which you know when you do all of that, upper limit, lower limit, the difference of the two, you get a pi over 3, and that happens to be the volume of this cone. But what are the most basic things you're seeing over here? You're starting out here with a function. You're starting here with, or you're provided an interval. You have a line of rotation or an axis of rotation. You do your radius determination. You can do a cross-sectional area and see what you're dealing with. Here we're dealing with a disk. You determine the area of that disk. You integrate the area of that disk from your lower limit to your upper limit, and you take it through and you do your definite integration procedure to give you your volume. There are two types of items which arise in terms of slices. You can get a disk, or you can get something which is called a washer, which is what we'll look at next, a washer. But remember, here we're looking here at a true rotational solid. Think about it. You have something which is being rotated, and it stays at a fixed point as everything around it rotates. It stays at a fixed point like a spinning top, so it's a rotational solid. Now the second type of movement you need to be familiar with is what I'll show you next, because a different type of cross-sectional slice appears. Here we have two functions. We have y equals x and y equals 1. We're looking here at everything in this video with regards to a horizontal line of rotation or a line of axis. You can have vertical, and it would not be much of a stretch of imagination. For anything which is vertically oriented in terms of your line of axis, you'd be doing integrations with respect to dy. You'd have vertical limits, upper and lower, and you do everything here with respect to y. So it's no different than what I'm showing you. And of course your equations would be x equals format, which we can talk about in another video. But here let's just concentrate on the basics. Always start out these type of questions with a good graph. We have y equals x, and I'm only drawing the limited domain portion from 0 to 1, 0 to 1. Then we also have a y equals 1, which is horizontal line. Again, I'm only drawing a limited domain from 0 to 1. Now we have two curves or two lines, and you can look at the area between these lines. And that's the region you're looking at. This is the region which will be involved in this dynamic movement around the x-axis. If you were to dynamically move this, look what you would end up getting. You'd get something like this, and here you'd get a volume determination for a three-dimensional object would look something like this. A good solid which has an inverted cone type of opening in it, and you see this portion right here is all open except you have this little solid portion here, but it all goes around circumferentially. But this is what you're looking at. When you have a structure like this and you do a cross-sectional slice of it, you don't end up having a disc, you end up having a washer, and that's what it looks like, a washer. You can see it, we can give it a three-dimensional nature to it, and this right here is my x-axis line going through it around which this rotation is occurring. But here the radius determination is a little more difficult because you have two types of circles which are forming. You have what is called an inner radius and an outer radius, because if you draw this across and you draw this across, you have from your line of axis an inner radius, and from this line of axis up here you have an outer radius. See, inner radius and an outer radius. Therefore you have to look at two different radii and two different area, and then you have to utilize both of them in your volume calculation. Think about it, your line of axis, here is my inner radius, and to the next line is my outer radius. My inner radius is from my line of axis to the first function, which happens to be y equals x. That's just the dimension of that inner radius. The outer radius is again from my line of axis to the other function line, which is y equals 1, and that happens to be that. And then you must have an inner area, which everything here is a circle, so you'll always be looking at pi r squares as your formula for your cross-sectional slice, pi r square. But here the radii are this. Inner area would be pi x square because the radius was x. The outer area here would be pi 1 square, which is just a pi. In these instances, when you have a washer, and let's write it out for you, a washer developing as a cross-sectional slice, you should be thinking about a formula which looks something like this. Again, from whatever limit to whatever limit, an outer area minus an inner area, which are integrated across your interval, and dx. And we have everything we need right here. We again can isolate the pi and push it out as a coefficient. We have our interval 0 to 1 provided. We have an outer area which is just a 1. You see there's a 1 attached to this pi, and then you have a x squared and dx. Now you just have to integrate this. It's not hard. You have a pi sitting outside, and let's do the definite integration. You have an x come out of there, and you have an x cubed over 3 come out of here from 1 to 0. And when you plug these in, zeros are meaningless. You have pi into 1 minus 1 over 3, and you get 2 pi over 3 as being the volume of this solid that you see. Again, this right here is not anything but a rotational solid. It's a true rotational solid, because if you were to look at it at this point, it's always fixed. This point is always fixed as it's spinning around like a top. So this, like the previous example, is a rotational solid. And again, you saw in this question we had slight complexity. The complexity arose here because of a cross-sectional slice, which is not a disc, but it was a washer. When you're dealing with washers and you have inner radii, outer radii, inner area, outer area, then you do the difference of the two to do your volume determination. So right now, in the two examples we've looked at, we've been talking about rotational solids. I want to end with not just an example, but just a simple explanation of what the difference is between a rotational solid and a revolutionary solid, and then that can be a subject matter of another video. So we end this video with this quick distinction between the two, rotational solid and a revolutionary solid. The procedure for volume determinations are the same, whether it's a disc or whether it's a washer. But the distinction is this: it's the manner by which the movement occurs. But keep in mind, many textbooks will even call these rotational solids. They'll blanket everything which comes under this topic as a rotational solid. I like to make the distinction because there is actually a distinction. If you think about a Earth spinning around its line of axis, like the Earth, the planet Earth, it's spinning around its line of axis, that's a rotational movement. If you're talking about the Earth orbiting around the Sun, then you know here we're looking at a revolutionary movement. But what is it in terms of a curve? If you have a specific, well, let's look at the same line, y equals x, from a limited domain, and you rotate it on the x-axis, you have a rotational solid. because this point right here will never move. It'll be like a spinning top, always fixed at this point as a three-dimensional structure develops. That's a rotational solid. In a revolutionary solid, look at the distinction again, y equals x, limited domain, but here our x-axis is not our line of axis, but we can say our line of axis is this y equals -1. Now we're doing movement around this. Now we're a distance away. We're at a distance away from this tip of this line, and then the reflection image will develop right over here, and our solid will look something like this. And you can see now there's a good difference. Here this point will remain fixed as it rotates. This point here will no longer remain fixed because it'll go here in this circular orbital movement as it moves around this y equals -1 line, simply because of the distance from right here to here, and from here to here there's no longer a fixed point that stays put as the rotation occurs. At all points this curve or at all points on this volume, there's a movement or a translationary movement, or you can say a translational movement about the line of axis. Hence you have a revolution going here in orbit. Here you have a rotation going around a fixed point. There's no rotation here around a fixed point because there's through and through rotational movement. And that right there is the difference between rotational and revolutionary solid, but the volume procedures will still be the same. That's it for this video. We're just introducing curve rotations, and this is a big topic and a very interesting topic, and we'll talk more about this later on. Thank you for watching. Have a nice day.